everybody, thank you for attending my talk today. My name is Ridhwana and I'm a senior software engineer. I currently work at a company called Dev. You may know it better as Dev.2 or at the Practical Dev on Twitter. And at Dev, I've been fulfilling my passion for coding, learning and sharing, and building communities. If you've not heard this accent before, it's one of the many South African accents. I hope that some of you have been to South Africa, particularly Cape Town, which is beautiful. If not, I hope that you'd visit sometime soon. In addition to my job, I also run a non-profit organization in South Africa called Kasimat. Kasimat is an after-school program that exposes students in under-resourced communities to STEM. Working within the environment of Kasimat has allowed me to appreciate the challenges that we as Africans face, and it's inspired me to firstly write this talk to share my experiences on a global level, and secondly build my own applications with performance at the forefront of my mind to compensate for the challenges that we encounter in developing communities. On this map, the countries marked in purple are developing countries. The darker purple is the higher income developing countries, unlike most of Africa, but they nevertheless are still developing. So why am I showing you this map? The reason is because whatever the challenges that Africa experiences, at least 80% of these developing countries, that is, all these countries marked in purple, they're experiencing it too. Which means if you don't build your apps to cater for emerging markets, these are the people that will either not be able to use your apps at all or will have difficulty using them. Living on the African continent, I have a lot of exposure to the challenges that we experience here, and I'd like to go through some. So the first challenge that I'd like to outline is load shedding. And load shedding is just really the bane of my existence and other Africans' existence too. For those who do not know what load shedding is, it's the deliberate shutdown of electrical power in part or parts of a power distributed system, generally to prevent the failure of the entire system when the demand strains the capacity of the system. I think they call it rolling blackouts in the US. But it's a little bit more impactful here. The implications of these is that there is no power for a minimum of 4 hours in South Africa on most days, rotating around the different parts of the city. This is a graph on the slide showing the plant breakdown of energy over the 2 months. It is absolutely insane to think that our plants break down as much. In other African countries like Zimbabwe and Zambia, as you can see from these tweets, the power has turned off unexpectedly for like around 12 hours at the time. As a result of having no power, we tend to have faint to no cell phone reception because the cell phone towers are being overused and are unable to handle this increased capacity during these periods. No cell phone reception means no 2G, 3G or 4G. Thus, without internet access, we are unable to use full functionality of applications. Another challenge that a large portion of Africans face is that we have very basic digital literacy. And this is probably due to the reasons that a lot of public schools have no computer labs and students don't have access to computers at home either. Hence, complex and unintuitive interfaces prove to be a hurdle. Data costs in South Africa are also extremely high, and they're also high in other parts of Africa. South Africa on this chart fits between China and Canada with about $10 per gig. You may say this is not too different compared to the US. However, $10 is not proportional to the earnings of South Africans who earn at least less than 50% as compared to employees in the US or Canada. While smartphones are common in Europe and Northern America, Sub-Saharan Africa lag in ownership. In South Africa, around 51% of people own a smartphone. However, this is below the median of 59%, whilst countries like Ghana, Nigeria, Kenya, and Tanzania are even lower. there is still a huge population of Africa that uses feature phones, which is more affordable than smartphones because they sell between $20 to $25. Being low cost, feature phones tend to have slower CPUs, low RAM, lower storage, older OS versions, and some of these devices can even be restricted to just 2G or maximum of 3G networks. Many contain outdated browsers and they often don't even have touchscreens. Instead, they have a keypad or D-pad for navigation. At Casimats, where most of the students have either no or low-end devices, they go to tech hubs in the community where their desktop computers and internet is provided. However, there is a time limit for the utilization of these computers. The internet penetration rates are between 75% globally, and in South Africa it's about just 59%, whilst other African countries like Ghana, Kenya and Tanzania are below 40%. The infrastructure is lacking in under-resourced communities in South Africa and other parts of Africa. Hence, very few have constant internet access. Instead, most people end up using 2G or 3G networks where they are able, but sometimes there's no connection at all. If we look at the statistics for the top apps that are downloaded in Africa on something like the Google Play Store, you will see that light versions of applications, when available, always end up being at the top of these statistics. We need to optimize for fast loading performance relative to devices. This means optimizing for CPU, memory, battery, and bandwidth usage. Before diving into some of these techniques to optimize performance, let's go over some important metrics typically used to measure performance of web applications or sites. These metrics can be measured at different phases of the loading cycle. So the first one is the first paint. The first paint marks the point immediately after navigation when the browser renders some pixels to the screen. Depending on the structure of the page, this could be displaying the background color or it could be the entire page being rendered. It simply depends on how the app was structured and how intentful they were about performance. We want to optimize most of the page being rendered. The first contentful paint is the point when the browser renders the first bit of content from the DOM, which must be text, an image, or just any element. For site visitors, this time signifies when actual content has been loaded on the page and it wasn't just like any change. The first meaningful paint measures when the page appears meaningfully complete. The first CPU idle marks the first time at which the page's main thread is quiet enough to handle input. And the time to interactive measures when a user can consistently interact, which means touch or click with all the page elements. So in the subsequent sections, I will be providing a high-level overview of some techniques that we can use to optimize for performance within emerging markets. They will include, firstly, reducing the bundle size, secondly, server-side or static rendering, the implementation of service workers, and number 4, just some other smaller tips. In each of these sections, we will reference the metric that we are optimizing for, and we will also give examples within the context of Ember where applicable. So let's dive right in. In modern times, most of our web applications are heavily reliant on JavaScript, and we ship so much JavaScript to users that it has become one of the most expensive resources on the web. We bloat our applications without thinking of the cost implication on both the hardware and the network of a user's device. The consequences of loading too much JavaScript on feature phones or low-end smartphones in emerging markets are substantial. On such devices, the JavaScript can end up blocking the main thread for a significant amount of time, thus increasing the time to interact with the application. In addition, the parsing of the extra JavaScript can result in a breakdown of that thread, causing applications to sometimes just run out of memory or hang or crash. This leaves the user with a feeling of extreme frustration, where he or she ends up clicking around the interface without seeing any effect. According to Eddie Osmani's article, The Cost of JavaScript in 2019, which I recommend that every person reads, he outlines how on mobile it takes 3 to 4 times longer for a median phone like a Moto G4 to execute Reddit's JavaScript compared to a high-end device like the Pixel 3, and it takes over 6 times as long on a low-end device like the Alcatel One X. Similarly, downloading bloated JavaScript and CSS files on a slow network connection increases the first meaningful paint time, thereby leaving the user with exactly the same feeling of frustration. According to Google's DoubleClick, when comparing sites that load in 5 seconds compared to sites that load in 19 seconds, the faster sites had 70% longer average session lengths, 35% lower bounce rates, and 25% higher ad viewability than their slower counterparts. That's a lot of increases. Knowing that the first meaningful paint and the time to interact is too high, if it's too high that users will leave our site and most likely not return, how can we then reduce the bundle site? So some very simple solutions include, the first one is minifying and concatenating your JavaScript build. We can improve on the overall performance of our sites and applications by minifying our JavaScript to reduce the file size and concatenating our relevant files to reduce the number of file requests. In Mbcli, we are fortunate that the JS files are already minified by default in production using Mbcli Uglify.js, and that all our files are already concatenated into just one JavaScript file. However, we can improve on this even further with code splitting. So, instead of shipping all the JavaScript at once, we can split the JavaScript by page, root, or component. This means that we can simply ship the minimum amount of JavaScript to prioritize what a user will need, and thereafter we can lazy load the rest. So we can fetch the additional bundles either in the background when the user is idle or in response to a user-initiated action. Whilst we haven't reduced the overall amount of code in apps, we have avoided loading code that the user may not use and reduced the amount of code needed during the initial load. Another common way that we end up bloating our JavaScripts is by importing loads and loads of add-ons. We just keep throwing it in there, and libraries into our applications. Instead, we could have simply gained the same functionality sometimes by writing just a small custom JavaScript function or by importing only a portion of that library. Importing only a portion of the library is now possible with tree shaking. With tree shaking, we can take advantage of static import statements to pull in only the specific and relevant parts of ES6 modules, hence eliminating dead code. It's possible to utilize code splitting and tree shaking from the Embroider v2 package. For those that don't know, Embroider is a modern, fully featured build system that works in tandem with Mbcli. It also newly embraces the ACMA standard for importing ES6 modules, which makes tree shaking achievable. However, it is important to note that Embroider is currently in beta, and there are some risks to be aware of it using it in production. You can read more about Embroider and their status on their status page. You can't improve if you don't measure. So some of the tools that we can use to audit our site include the Google Chrome's Lighthouse tool for performance audits. There are 3 audits that will be useful to look at whilst reducing our bundle size, and they are very aptly named. So the first one is JavaScript boot time is high audit, and that reveals how much CPU time each script on the page will consume, along with its URL. Then the unused JavaScript audit, which reveals the JavaScript downloaded by the current page, but it shows the JavaScript that is never used. The minified JavaScript audit, which will compile a list of unminified resources that it finds on the current page. From there, you can simply take action by minifying those files manually or augmenting your build system to do it for you. So the second one that I can think of is the Mbcli bundle analyzer. The Mbcli bundle analyzer analyzes the size and the content of your Ember app's bundled output using a really cool and easy to understand visualization. More specifically, we'll be able to see which individual models make it into your final bundle. So if you look at the picture, you'll be able to see that it shows which are the different packages that have gone into your bundle. We also can find out how big each contained module is, including the raw source, the minified, and the gzip sizes. Finally, by looking at the diagram, we can kind of see which of the packages have made it into our bundle by mistake, and then we can optimize our bundle size. The third one is bundle phobia. And so before I actually install a bundle to my application, I like to know how a bundle will impact my size. Bundle Phobia does this by showing the cost of an NPM package by providing the information on the size of the package, how fast it downloads on 2G, and how fast it downloads on a 3G network, and what percentage of other dependencies that package comprises of. Thus, we can then make informed decisions on whether to edit or not. Whilst JavaScript single-page applications can be quite snappy once they are fully loaded, there is this time between load and time to interact where users are usually presented with a blank screen. This is because for most single-page applications, the initial document returned by the server is empty, thus resulting in an increase in the first contentful paint. So what if we wanted the best of both worlds? A quick initial load time, but also just snappy successive interactions. This is achievable using server-side rendering or static rendering for all or most of the popular pages in your applications. This can result in an almost instant first contentful paint, which is particularly useful for developing countries where network connections may be unreliable. Remember that the first contentful paint, which we discussed in one of the earlier slides, measures the time from when the page starts loading to when any part of the page's content is rendered on the screen. Using this technique, we are then able to display useful information, that is, content, to the user instantly. When our first contentful paint is less than 1,000 milliseconds, users are really happy. When the value is between 1,000 to 3,000 milliseconds, so 1 to 3 seconds, users are usually a little bit less pleased, but still pretty happy. But over 3 seconds, so say 3 to 5 seconds, starts causing frustration. So over 5 seconds, users have just completely lost interest. It's really simple to server-side render pages in Ember. And also, all we need to do is to just use install fastboot and Ember, which actually static renders the application and allows us to pre-render any list of URLs into static HTML files at build time. As a result, the pages can be served statically, and it has a fast first paint of the HTML content from fastboot. So all we do is we install Mbcli fastboot, we install Ember, and then we can configure the URLs that we want to pre-render. Now that it's set up, we can simply even just see the HTML via curl. Since the most important values here was the first contentful paint, we can run the performance audit once again, and we notice how the value decreases. We see the value from the Lighthouse Chrome tools. It's great progress that we are able to render our assets and our content optimally, especially to ease the burden of slow network connections, high data costs, in case of low-end devices. But what about taking it one step further? Service workers and caching can reduce users' data costs even further, and they can render pages even faster with the least amount of processing time. Not only that, but we can also render our applications offline for those sporadic connections during load shedding or whilst passing through poor network areas. A service worker is essentially a background script that runs separately from the main browser thread, responding to events including intercepting network requests, caching or retrieving resources from the cache, and delivering push messages. The implementation of service workers is pretty simple using Ember and its add-ons. So here's a very brief look on how to integrate service workers into our application. The Dockyard Ember service worker documentation makes it really easy. We use the following commands. So you'll see the first one is Ember install service worker, which just installs the service worker when the page loads. Then we do Ember install service worker index and the service worker asset cache, which essentially caches our indexed HTML page and all the other static assets. So at this point, if you had to disconnect your internet connection or turn into an offline mode in our browser's dev tools and refresh the page, our app should still load. Then we can take it one step even further, where we can install Ember Service Worker Cache Fallback, which then caches any non-static resources like requests to the API. And just like that, our service workers would be up and running. We just need to browse the app for a few moments whilst online, and we'll essentially be priming the fallback cache. And afterwards, we can put our browser into offline mode and try to load a page that we have visited before. And guess what? It should now serve your API responses from the cache. But we can make our applications even more functional. I mean, if I think about it, when I'm without internet during times of load shedding, I not only want to view data, but I might want to fill out forms or bookmark some data, or maybe even send some information through to the application. I have the memory of a goldfish, and once I close an app, I'm really not going to remember to come back to that app. So this is where Ember Pouch comes into play for us, and it basically is data persistence. Ember Pouch allows data to sync automatically once a connection is restored. In the background, the data is saved on the client side using IndexedDB or WebSQL, and we just keep using the regular Ember Data Store API. Once again, in order to test our improved performance and offline strategy, Lighthouse comes to the rescue. You can see your cache files, and you can use network requests to determine where the request is getting answered from. Is it from the cache or the API? And you can also use something like Google Analytics to track metrics that will help us to assess the impact of our service worker. Finally, we come to other performance tips. So there are a couple of techniques that I'm not able to explore as deeply, but I'd still like to list some of them out because I believe that when they are used appropriately, they will provide better accessibility for emerging markets. Some of them include, firstly, using SVGs where we're able to, or else optimizing images by using tools like Squish or Image Optimizer. HTML source sets are also really useful to serve different images to different visitors. A company called FontSpace reduced their image payload by 86%, resulting in a reduction in load time of 65%. This improved user experience helped double FontSpace e-commerce purchases conversion ratio, cut bounce rates by 20%, increase mobile revenue by 7%, and dramatically improve SEO. Optimizing and sending through only the necessary keys in our JSON payloads can really just optimize our network requests in our JSON. We should serialize and compress adequately as well. In addition, adopting a technology like GraphQL would automate the optimal parallelization of data fetches, thus increasing the performance. Instagram increased impressions and user profile scroll interactions by decreasing the response size of the JSON needed for displaying comments by 33% for the median and 50% for the 95th percentile. And finally, we can use techniques like adaptive loading to tailor the experience based on the user's constraints. Adaptive loading uses signals to determine the network, CPU, core count, and memory. And based on those values, we can then conditionally load more highly interactive components or run computationally heavy operations whilst not sending these scripts down if you're on a slower device. However, it's useful to note that the web properties that are used to determine network, CPU, core count, and memory are not available via the web API to all, especially older browsers. This unfortunately does not make it extremely useful for African markets as yet, but it is a useful technique that most likely will be used more commonly in the near future. Using all or most of these strategies that I've outlined allows us to build more efficient applications that will deliver an improved experience within Africa. However, our professional environments usually consist of teams that include multiple developers working on one application together. Within these teams, not all developers are knowledgeable or even mindful of performance. So, how do we go about proactively maintaining a code base with the team for just optimal performance? This is where performance budgets integrated with the CI tool become really useful. So, what is a performance budget? A performance budget is a limit for the pages or components which the team are not allowed to exceed. Eddie Osmani, the performance guru, mentions the 3 important metrics that we should use in order to incorporate this budget. The first one is milestone timings, which are based on the user experience when loading a page. So things like time to interactive, first contentful page. It's that first page of metrics that I showed you when I started the presentation. We may need to pair several of these metrics together in order to represent our full story. Then there's quantity-based metrics. So these are based on raw values. So the weight of the JavaScript, the number of HTTP requests. These are directly correlated to a browser experience. And finally, we have rule-based metrics, which are scores generally by tools such as Lighthouse or Web Page Test. They often just provide one single number on a series to grade the site. Furthermore, we can apply different budgets to our mobile applications versus our desktop applications versus device classes, because their underlying hardware like CPUs and memory and their connection capabilities differ across these different experiences. So, an example budget on my personal website could include something like the homepage must ship less than 170 kilobytes of JavaScript on mobile. It should include less than 2 megs of images on a desktop, but maybe 500 kilobytes on mobile on page load, and then we can lazy load the rest afterwards. It should load and get interactive in less than 7 seconds on an Android Go, which is one of the more popular devices in sub-Saharan Africa. And also, maybe the score needs to be greater than 80 on a Lighthouse performance audit. These are just some examples of what I could put into my performance budget. It is useful to note that there are some standards which we can adhere to, like for mid-range mobile devices with slow 3G connections, a good target for first loads is to load the page and be interactive in 5 seconds or less. For subsequent loads, a good target is to load the page in under 2 seconds. This is where the developer has the opportunity to set the precedent to be inclusive to other emerging markets. But the most tricky thing about creating a budget is usually to come up with the performance metrics themselves. One way to do this is to use a calculator like performancebudget.io to get some baseline and then configure the budget based on your knowledge of the type of application being created as well as your target market. This here on the slide is performancebudget.io, and it's a really good experience. Once we've crunched the numbers, we want to also proactively stay aware of these numbers throughout the development process. This can be done by integrating something like Webpack Performance Hints, which issues command line warnings or errors when the bundle size grows over the limit. This is perfect for your development process. Thereafter, once we start deploying, we can integrate it with the CI to automatically enforce size limits on pull requests for teams. So if the test fails, we can simply prevent the pull request from being merged. Some CI options that can be used is the bundle size CI and Lighthouse bot. Finally, I recommend also using SpeedCurve for the reactive monitoring, so that we can actually monitor some real users, so that we can improve based on some baseline. As a result of using a performance budget and these integration tools, developers on the teams have performance at the forethought of their minds, and hence they tune their development practices accordingly. In conclusion, yes, this graph again, there are really no downsides to make your application's performance. There are only benefits. A performant application opens you up to a whole new market. This is millions of additional people. It is also a proven fact based on statistics and case studies, some of which I've cited in previous slides, that performance app increases traffic to your sites and keeps users engaged for longer periods. On a fast site, users are known to consume more content. Some of these changes, especially server-side rendering or even static rendering, allows our apps to have enhanced SEO, thus increasing our leads and sign-up conversion rate. In fact, a study shows that rebuilding Pinterest pages for performance resulted in a 40% decrease in wait time, a 15% increase in SEO traffic, and a 15% increase in conversion rate to sign up. Finally, for avid travelers like myself, PWAs are hailed lifesavers. I mean, who doesn't want to be able to check the train schedule or navigate around a city without any network? I know I do. With that being said, I hope I've now convinced you to think about performance and expanding your apps to the African soil. Why not? Thank you so much.